Standard deviation. So this begins our conversation talking about the variation of a data set. So we've talked about the center with mean, median, and mode. We've talked about the shape of a graph, symmetric, left skewed, right skewed. Now the third piece of the puzzle is variance. So the first definition here is a range. It's the difference between your maximum and your minimum data entries in your set. It must be quantitative, so they've got to be numbers so that you can subtract them. So the range is truly just max minus min. So here's our first example. 2 corporations each hired 10 graduates. The starting salaries for each graduate are shown. Find the range of starting salaries for Corporation A. So this first set is Corporation A. So if we're looking through here, we're trying to find the smallest number, our minimum. So 37 looks like our minimum. And then we also need to find our largest value, which I think is this 47 max. So to find the range, it is just max minus min. So 47 minus 37, our range is 10. Now, while we're looking at this, it only asks for Corporation A, but we're going to do Corporation B too, just to compare it. So if we look for our maximum in Corporation B, looks like our maximum is much bigger. It's 58. And our minimum is 23. So in this case, if we do our max minus min, we have 58 minus 23. That's the 35 for range. So if we had found a little bit more about these two data sets, they both actually had the exact same mean and median, and even a mode of 41. Yet we just found when we did our variation, those two numbers were very different when we found the range. The difference is the entries in that second set had a greater variation, or a larger spread of numbers. As you can see in the figures on our next slide, the starting salaries for Corporation B are more spread out than those for Corporation A. So when you're looking at a graph, you see data that's tight together. For Corporation A, it had a smaller range. And then a data set that has like a larger spread from max to min had a larger range, more variation, more spread out. So that's what this section is all about, is trying to describe numerically what's going on when we talk about a spread of a data set. So the next definition we need is the deviation. It's your difference, which means subtraction, between each one of your data entries and the mean of the data set. So you're trying to find how far each data value is from the average for the set. Now, if we had a population data set, remember population means we have all entries, then we're going to use x minus mu. This is our population mean. And if we have a sample to our data set, remember it's some or a subset of your population, some of your data is missing. It's technically the same math, the symbol just changes because x bar represents your sample mean. So you're going to see a little bit of notation changing. The math is not very different between the two. There is only going to be one difference between them when we get to standard deviation. But do keep an eye on those notations and variables as we go. So in order to find our standard deviation, we actually find our variance first. And then from our variance to our standard deviation, all that we do is we take a square root. So it looks like we have two separate formulas here, but if you look underneath that radical, they are exactly the same. So population variance is this lowercase sigma squared. Population standard deviation is this symbol right here, the lowercase sigma. Now to find this, you're going to be doing this formula, but it's more of like a reminder of the process. So there's a number of steps that you need to do to get that result. It's not just a plug and chug. So a couple observations about it. The standard deviation is measuring that variation or the spread. So it's going to have the same units as our data set. So if we're talking about inches, then our standard deviation is in terms of inches. Your standard deviation, so that's SD, is always going to be greater than or equal to 0. You can't have a negative spread. So it's always going to be 0 or bigger. If your standard deviation was 0, it means that all of your values in your data set all were exactly the same. There was no difference between them. So maybe your data set was like the number 2 repeatedly. So if there's no spread, your standard deviation is 0. And as your entries get farther away from the mean, more spread out, the value of your standard deviation increases. So as your range goes up, your standard deviation goes up. So here are your steps in order to get to a standard deviation. We start by finding your mean. Then we find the deviation. So each one of those x's minus the mean, and you do it for all values. Then you go through and square all of those. So each one of the values, you're going to then square that deviation. And then with number 4, you add them up. That's what that capital E looking symbol, it's called your sigma. You add them all up to get a single number here. So this is where we go from having a data set in a chart to a single value. And we're going to take that single value and divide it by n. And just as a reminder, that is your sample size. So we're going to divide it by our sample size. And this is what's called your population variance. And the last step we need to get to our population standard deviation is we throw that big old square root on there. We square root it. So here's our first example. Find the population variance and standard deviation of the starting salaries for Corporation A listed in the first example. So we have our sample size is 10, so n equals 10. And if you added up all of those x values, you get a sum of 415. So the first thing we need to find is our mean. And since we're talking about a population, we use mu. It is the sum of all of our numbers divided by our sample size. So 415 divided by 10 is 41.5. This is our mean. So that's the first step we have in trying to find our variance and standard deviation. Now that we have that number, to find deviation, you're going to take each item in list 1 minus that 41.5. So I've got my calculator here. So 41 for that first row minus the mean gives me negative 0.5. 38 minus 41.5 gives me negative 3.5. You're repeating the same process down the whole column. So you're taking your x, that's your first column number, minus the same mean value for each. So each one of these minus the mean, 41.5. Now, once you get through all of your deviations, you could check it by adding them up real quick. So I'm adding up this whole second column. And every single time you should get 0. So what that tells you is that you had the perfect mean. It was right in the center of all your data. So you should have an equal number of things that were bigger than that number and an equal number of things that were smaller than that number. So there should be a mix of positive and negative numbers through this whole column. But that's kind of a dead end if every problem goes to 0. So that's why we have our next step. We've got to square all of these values. Squaring means all of these values are going to be positive. It's going to change the number a little bit, but they are going to all be positive. So when we add them all up, we're going to have a number we can work with here. So keep in mind with using your calculator, Make sure you put parentheses around the number that you are squaring so your calculator says the right number out. So negative 0.5 squared gives me 0.25. Negative 3.5 squared gives me 12.25. And it's nice if you look ahead and you see any repeats in your column. Whether they were positive or negative, they should come out with the same answer here. So filling in some repeats. So 2.5 squared is a 6.25. 5.5 squared is 30.25. And 4.5 squared is 20.25. Once you have your entire column, everything should be positive. Go ahead and add up all of your numbers. And we get 88.5. So this is the sum when we add them all up from the column. So now we've kind of put all of our numbers together. It's called the sum of squares. And our next step to get our variance is we need to divide it by our sample size. So just as a reminder, there were 10 items in here. So our n was 10. So we are going to take that 88.5 divided by 10 to get 8.85. This is our population variance. Now, this is not in the context of our same units as our original problem. This is a good stopping point to just point it out, name what it is, but all of our problems are going to take it one step farther. The goal for us is to find that standard deviation. So the next thing you need to do is you need to take the square root. So square root of 8.85 and I get in the habit of writing 4 decimal points when I'm doing my own work. So 2.9749. This is your population standard deviation. This is the goal. Now, what we just found was a population standard deviation. Now we need to do it with a sample. So the only thing that changes besides the notation, so you should note that there's a X bar in there instead of a population mean. So this is for sample, is that on bottom, for both of these, we're dividing by n minus 1. So not the full sample size, it's the sample size less 1. But otherwise, all of our steps are the same. So we're going to find the mean. We're going to take the mean and subtract it from each one of our data entries. We're going to square each one of those, add them all up, divide by n minus 1, and then square root to get that sample standard deviation. So here's our problem. It says in a study of high school football players that suffered concussions, researchers placed the players in 2 groups. Players that recovered from their concussions in 14 days or less were placed in group 1, and those that took more than 14 days were placed in group 2. The recovery time in days for group 1 are listed below. Find the sample variance and standard deviation of the recovery times. So for this data set, we had a sample size of 12. If we added up all of our x's, we had 90. So in order to find your mean, you're taking that 90 divided by the 12 to get 7.5. Now, in order to calculate your sample standard deviation and your sample variance, Keep in mind that we need to divide by n minus 1. So in this case, if you take 12 and subtract 1, you're using 11. Now to find that sum of squares, we can use our calculator for this. So you might notice there's not a chart on here. So under stats in the edit, under list 1, you can type in all of your data. So all of those values on the previous page, all 12 of them. And then at the top of list 2, you can type in L1 minus 7.5. And if you type it at the top and then click enter, it will auto fill in the deviations for the entire column. It's a pretty cool trick. Now, you've got with that second list, the deviations. To find them squared, you go to the top of list 3 and you type in at the very top, list 2 squared. When you click enter, it will auto fill in that entire column with all of your squared values. Now what we're looking for next is the sum. We want to know the total from that column. So the quickest way to get it is to go into stat, go right arrow over to calc, and you're looking for that first option, one var stats, and you're going to set it for list 3 and calculate. Once you do, what you're looking for is sigma x. That will tell you quickly that total of list 3, which is the number we're after, and what you'll find, it's the number 39. So feel free to pause, go through those motions, and check yourself here. Once you have 39, that's the sum of your deviations squared. We're going to divide it by our 11, so that's our sample size minus 1. And I'm running out of space, so I'll write it over here. We get for variance 3.5455. That is your sample variance. And the last step we need to do in order to get a sample standard deviation is we need to take the square root of that number. So if we square root our variance, we get 1.8829. That is our sample standard deviation, which is a letter S, lowercase s. So here's another example. Sometimes people prefer to do these by hand with a chart, but you're going to get to a point where your data set is so big that it would be a very large chart to try to do this entirely by hand. So feel free to try the chart with a smaller data set and you'll get some practice in your homework, but definitely make sure you pull out your calculator and practice doing this with the calculator. So this one says sample office rental rates in dollars per square foot per year for Los Angeles are shown in the table. Use technology to find the mean rental rate and the sample standard deviation. So the first thing we need to do is we need to type all of this into your data, all of this data into your calculator. So into list 1, you're going to type the data. Now in order to find the mean of this data set, you're going to go to one var stats, and you're going to set it for list 1 and click calculate. And at the very top, you're going to see the mean. Once you have it, to go through the motions to find your sample standard deviation, you're going to go back into your list, and at the top of list 2, you're going to type in list 1 minus whatever value you got for your mean. When you click enter, it will autofill that column. And then you're going to go to the top of list 3. You're going to type L2 squared. This is where you're going to square your deviations and click enter to autofill. Now we want to know the total of that column. So we're going to go to one var stats for list 3. And what we're looking for is sigma x. We want to take that number divided by our sample size minus 1, and that will give you your variance. Once you have it, square root your variance, and what you should end up with is your sample standard deviation, which is 17.3914. That is the letter SX, or most of the time we just say S, lowercase s. Now, just to give you a visual again with standard deviation, the larger your range, the larger your standard deviation. So just side by side, here's a couple just visuals. If you have a standard deviation of 0, there's no spread. That means all of your data is the exact same number. Doesn't happen very often. So as your standard deviation gets a little bigger, there's a little bit more spread. As it gets bigger again, there's more spread again. So from 2 to 8 versus 3 to 7. The more the entries are spread out, the greater your standard deviation. Those two are connected to each other. Now, once we have this number, the standard deviation number, we can sketch out on a graph your mean and your standard deviations, and we can use the empirical rule to talk about percentages of your data set. So for data that is symmetric or bell-shaped, we can say the following rules about it. We could say that 68% of your data lies within one standard deviation of the mean. What that looks like is you've got your mean in the middle, and you add one standard deviation to get to this spot, and you subtract one standard deviation to get to this spot. We're saying that this distance represents 68% of your data. Now we can go one farther. If you go out 2 standard deviations to both directions, so to the right and to the left on a number line, now we're talking about 95% of your data. And if you go out 3 standard deviations, we're talking about the majority of your data now. That's 99.7%. Now, this next slide has a very nice image of this, where you've got your mean in the middle, and it shows you going out 1 standard deviation, you add it in. If you go out 2, you add it in twice. If you go out 3, we're adding standard deviation in 3 times over there. Same thing to the left on your number line, you just subtract as you go to the left. So on a sketch, these bars are equal distance from each one of these markings. Now, when we add the empirical rule to this, then what that says is these 2 blue sections together represent 68%. Or if you cut that in half, each one of these slivers is worth 34%. Keep in mind this is symmetrical, so we can cut it directly in half to get these smaller components of our normal curve. If we go out 2 standard deviations, then both the blue and the tan, all 4 of these sections add up to the number 95. So if we have that the middle 2 are each 34, and then we subtract that from the 95 and cut it in half because it's symmetric, then these 2 sections are each 13.5%. So all 4 of these together add up to 95. And if we go out 3 standard deviations, these 2 green slivers are each worth 2.35%. Now, the one thing that you don't see is there's a tiny little piece underneath these curves on the end, and those represent 0.15%, a very, very tiny little bit. But by adding those 2 pieces on the end, we add up all of our percents together, it's going to equal 100%. Everything has been accounted for. So this is what a problem would look like when using the empirical rule. This example right here says, in a survey conducted by the National Center for Health Statistics, the sample mean height of women in the United States, aged 20 to 29, was 64.2 inches, with a sample standard deviation of 22.9 inches. Estimate the percent of the women whose heights are between 58.4 inches and 64.2 inches. So what we want to do is make our own little sketch of that normal curve, where we start in the middle with the mean, 64.2. Now we can sketch this out fully with 3 standard deviations to the right, 3 standard deviations to the left. But always look and see which section they want. That way you don't have to go in both directions unless you need to. So both the numbers I'm looking for, 58.4 and 64.2, are going to be to the left. It's right where we are at with our mean and something smaller. So if we take our mean, 64.2, and subtract the 2.9, that's our standard deviation, we get the number 61.3. So that's the next marking on our normal curve. Now that's not quite the number we want, so we've got to do it again. So subtract again from it 2.9, and our next number should be 58.4. That is what we're looking for. So once you find the markings that you're looking for, it will be one of these lines. It'll never be in between. Then what we want to do is find the percent of women between these two numbers. So we want to know the percents in these two sections. Now, referring to the last slide, that was a blue sliver and a tan colored sliver. So the blue sliver was 34%, tan covered sliver was 13.5%. We add them up together, then we have 47.5% of women between those two sizes. That's what we're looking for. Those percentages, the 68, the 95, the 99.7, or if you want to think about them already pre-split as the 34, 13.5, 2.35, and 0.15, either way, those are standard for all problems. So it has nothing to do with this specific problem. It works on all of them this way. So the last thing we need to cover here is for grouped data. So if we were trying to find a sample standard deviation for a frequency distribution, if you glance at the problem, you'll notice everything looks the same as what we've done before. And I'll take that off what I just scratched off. The only thing we're adding is our frequency. So the letter F. We've got to multiply that in here. So when a frequency distribution has classes, so those ranges from one number to another, lower to upper class limit, estimate your sample mean and standard deviation by using your midpoint. You need some way to describe the middle. We need an X value for each. So here's our example. The figure shows the results of a survey in which 1,000 adults were asked how much they spent in preparation for personal travel each year. Make a frequency distribution for the data. Use the table to estimate the sample mean and the sample standard deviation of the data set. So we have a bunch of intervals, so like 400 to 499, and then the frequency with it, 300 to 399 in the frequency. So we're going to take all of that information and put it into a chart. So we have our classes filled in and we have our frequencies. So the first thing we need to do is get from classes to an X value. We're going to use midpoints. So keep in mind, to find the midpoints, you are going to add your two endpoints. So add 0 plus 99, then divide by 2 to find the center, and that's your midpoint. And you're going to do that for each one of these rows. Now for this last row, because it's got a plus sign, it's kind of open-ended, we are going to use it as if it was 500 to 599. So we're going to find the midpoint of that. And there they are. They just popped up. So now that we have our midpoints, the next thing we need to do is take our midpoints times our frequency to get this XF value. So these numbers are going to get a little big because we have big numbers we're working with. There they are. Now, we need to find some totals here. So if we add up all of our frequency values, so everything in this column right here, this is our sample size. So this is our N, and it's 1,000. So sometimes they will tell you in the problem that you have 1,000. Sometimes you have to find it by adding up your frequencies. And we also want to know the total of this last column, the sum of each of your data values times that frequency. And we get this right here, the 188,500. So the first thing we're doing with this is we're finding that sample mean, taking that total divided by your sample size. So again, the 188,500 divided by 100 equals your mean. So our mean is 188.5. That was our first step, find the mean. Now we need to find deviations. So we've got a new chart here, and just as a reminder, these were your x values. These are your midpoints. So you're going to take each one of those minus your mean. So minus the 188.5. Then we're going to take all those numbers and square it. So that's what's going to make all of them positive. Get them a little bigger. And here's that new piece that we're adding. Again, because it's a frequency distribution, we are multiplying that column by each one of those frequencies. So if you want to hop back to the previous slide just to refresh your memory of those frequencies, that is each one of these items right here times the frequency for that row to get these numbers. Again, I know they're getting big. We're almost there. We add them all up. We want to get the total. So we get 22,979,000. That's your top number divided by n minus 1. N is our sample size of 1,000. So we're going to divide by really 999. So I'll throw that bar in there again. You're dividing, and then you're taking that square root. And this is your final answer. This is your sample standard deviation for a frequency distribution.